All right, am I on? I'm on. Let's get started. Welcome to Data 8, lecture number 10. Today we're going to be talking about functions. Some announcements. So I forgot to mention yesterday that we do have this resources page on our website. And if you happen to scroll down the resources page, you can see this convenient list of table methods, functions and methods that you can use to reference. So we've been learning quite a few methods that we use for tables. If you need one place to kind of look at what everything does, darn. OK, make sure my screen's on. What about now? What about now? Sweet. All right. So as I was saying, if you go to data8.org/summer17 and you go to our resources page, there is a convenient list of table methods. So you can scroll down here, be like, oh, OK, select does this, drop does that. I have a bunch of other methods here. There are some methods here that we haven't learned. Don't worry, we'll get to them. But for now, this is probably something that you can use to keep track of all the stuff that we've learned so far. If you want something more detailed, you can go ahead and click on the midterm study guide. I believe that links to another convenient reference sheet. So here is kind of like a brief overview of the stuff that we covered in class. So here's statements, arrays, functions, which we're going to cover today. And I believe here we also have more functions and then more table methods. OK, so lots of quick, easy references and cheat sheets for you. Hope that's convenient. Cool. What else do I got? So if you were in lab yesterday, there was one widget that unfortunately was not working. It is now working, but you'll have to open up the lab again and rerun that cell to see that widget. It's not super important, but if you want to see what that widget would look like, you can go ahead and rerun that cell. It was broken yesterday. Sorry about that. Finally, there's no lab on Monday or Tuesday of next week because of July 4th holiday on Tuesday. However, there is lecture on Monday, so I'll see you on Monday. Any questions? Cool. So let's start off with a question for you. This histogram describes a year of daily temperatures. Try to answer these questions. What proportion of days had a high temperature in the range 60 to 69? What proportion had a low of 45 or more? And how many days had a difference of more than 20 degrees between their high and low temperatures? So these are a bunch of days in a year. And we've recorded down the high and low temperature for each day. And we've plotted an overlaid histogram of the lows and the high temperatures. Go ahead and introduce yourself to your neighbor, and then talk about these 3 questions. If you're not next to someone, you can scooch over to be next to someone or talk with a person behind you or in front of you. You have many options. We live in a 3-dimensional world. The units for the vertical axis are percent per unit, as we've discussed before. That's 48 out of 48 out of 100. Yeah. OK, anyone have any guesses for the first question? What do you guys think? Let me get 2 volunteers. Just say out your number. What did you think for high temperature in the range 60 to 69? What proportion? Yes.
We thought about 48%.
48. OK, one more. If you got 48 and you were scared to say it, now is a great time to say it. Yes.
Affirmative.
Affirmative. We have two 48s. Okay. What about a proportion that had a low of 45 or more? What do you get? What do you think, Alan?
We didn't have the actual data, but we guess it's around like 85%.
You guessed that it's around 85%. Okay. Any other takers? Yes, behind.
We guessed around 72%.
We guessed around 72%. Okay, so 85, 72, around there. Okay, so what about the third question? What did you guys think about the third question? Anyone have any opinions on the third question? Well, it makes sense that you guys don't really have an answer for the third question because you can't answer the third question with this histogram. Okay, so let's talk about it. So what proportion of days had a high temperature in the range 60 to 69? Okay, so what we do here is we look at the range 60 to 69, and we say, okay, we know that the area of the histogram is a proportion of stuff within that range. Okay, so we look at the width times the height. The width is 10. The height is around 48, so we get around 48% of days had a high temperature between 60 to 69 degrees Fahrenheit. Okay. Now let's look at what proportion had a low of 45 or more. Now you can do the same thing here and add up all the bars. A faster way to do it would be to kind of look at the bars to the left, right? So you take this area right here instead of like this big area right here. So you just take these bars right here. It looks like this is like 2, this is 1, this is like really close to 0. So maybe like 5 times 0.8 is like 5 times 0.8 is like 4%. Plus another maybe like 10% here. So somewhere around like 80. So you have like maybe like 15% of your total area here. And then to find an area on the other side, you do 100% minus 15%. You get around 80, 85%. Somewhere around there is fine. Okay, so same deal. Find the areas. In this case, I can use a little shortcut. I can do 100% minus the left-hand side to get the area on the right-hand side. Finally, the third question, how many days had a difference of more than 20 degrees? Well, I can't answer that with this histogram because this histogram is just showing me, oh, the lows are somewhere in this ballpark, the highs are somewhere in this ballpark, but it doesn't let me compare individual days. Okay, that's not the question you can answer with this visualization. Yeah, name and question. Annabelle.
What's the vertical unit?
So Annabelle asked, sorry, what's the vertical unit? Unfortunately, it's not labeled here, but whenever we deal with histograms from now on, we'll just assume that it's percent per unit, like we've discussed yesterday. So we will very rarely see like the normal counts that we've done yesterday. We'll almost always just use a density scale, so we can almost always assume the vertical axis is percent per unit. Sorry for not making that clear, though. Good question. All right, let's keep going. So today we're going to be talking about defining functions. Now we've discussed a bunch of functions that we use in this class so far. So for example, abs, max, min, round, all of that stuff. Those are functions that are already defined for us, so we can use them out of the box. But oftentimes it's convenient to define our own functions. Let me show you why. Okay, so that's run that. All right, so let's suppose that I'd like to convert. So first of all, we've seen these guys. Okay, so add max to 3. Okay, so these are Python's built-in functions, so the ones that are already available. Let's suppose that I want to convert some numbers from degrees Celsius to degrees Fahrenheit. Okay, so let's take the boiling point of water, which is 100 degrees Celsius, convert it to Fahrenheit. So we times 9/5 plus 32, and we get the boiling point of water in degrees Fahrenheit. Okay, I can also take the freezing point of water. So 0 times 9/5 plus 32. Okay, great. Let's suppose I want to take one more, the room temp, like the room temperature in degrees Celsius, 9/5 plus 32, I get around 69 degrees. Okay, so I'm doing this a bunch of times, and I'm saying to myself, well, I'm converting 3 numbers from degrees Celsius to Fahrenheit, but it looks like what I'm doing here is pretty much the same in every cell, right? So in these 3 cells, what I'm doing is pretty much the same thing. I'm just taking whatever is here and then changing the numbers on the left-hand side to convert from Celsius to Fahrenheit. Usually when you're programming, if you find yourself repeating your code a lot of times, typically there's a better way to do it. And in this case, the better way to do it is to define a function. Okay? So the way functions work is they basically let me say, okay, they basically let me separate out which parts change in this code from which parts stay the same. Okay, so To define a function, I write def and then the function name, so Fahrenheit. And let's call this x. And I will return. So what I can do here is I can just copy that in, but replace the 21 with x. And this says that when I call the function Fahrenheit, I'm going to replace the value x here with the value that the function gets as an input. Okay? So when I run that, I can now do the same thing, Fahrenheit 100, and I have 212 degrees Fahrenheit. Cool? So this should be familiar to you if you went to lab yesterday or today or worked on lab otherwise. But I just want to let you know like why these functions exist. It's not just because we're teaching you something that looks cool. It's because it actually saves you a lot of time. Okay? So you find yourself repeating yourself. You find that you need to do a lot of repetitive stuff in computer science. Functions allow you to do that much faster. Okay. So just to recap. So the way functions work, again, is if you have a function that looks like this, we write def and then the name of the function. And then in the parentheses, we write down the argument names. Okay? So we say this function spread takes in an input, and we call that input values. Don't forget the colon here. So you get a syntax error if you forget a colon. Make sure the colon is there. The body of the function is just whatever lines of code are inside that function. And right here is what we say, OK, when we call this function spread takes the variable values and then returns max of values minus min of values. It returns that value out. So that's the output of the function. Okay, so input of the function, output of the function. Any questions about that? Cool. So let me point out some gotchas when it comes to writing these functions. Okay, so let's say I'm going to call Fahrenheit a couple times. So there's a freezing point of water. Very nice. I can also define my own variable. Fahrenheit, oh, okay, Fahrenheit, okay, y over 4. And what happens is, again, when Python evaluates this, parentheses come first, so it does y divided by 4 to be 25, and then it calls Fahrenheit on the value 25. I get back out the value 77 degrees, okay? Now, what happens if I ask for the value of x? Kevin?
Because x is locally defined within the function, I suppose if you call it, it's going to give you some type of error because once once the function is finished in terms of doing its job, I guess the value of x gets thrown away. Is that true?
Yeah. So Kevin guesses that the value x is only available in the function, and that's absolutely correct. So if I run this now, I get a name error because x is not defined. Now you look at this and you're like, OK, what's going on here? Because I used x completely fine in here. And that's because when I'm inside a function, any variables that I define and arguments that are passed in are only available inside the function. Okay? So although in the function, because in the function I had the value x, I can use the value x in the function. But outside the function, no deal. Okay? So no value of x. All right. So now let's guess at what happens if I say x equals 25, and then I call Fahrenheit on x. What do you think will happen here? Talk with your neighbor for a minute about what you think the result of this will be and what the value of x will be afterward. Go.
Well, that's okay, but you can get confused.
All right, let's find out. So I'm going to run. And indeed, I get Fahrenheit of x. X becomes 25. And I call Fahrenheit. I get 77. What is my value of x? My value of x is still 25. Okay. Now let me ask you another question. What happens if I do x equals 10 in my Fahrenheit function, and then run this? Oh, sorry. And then I run this. So when I call it, I get x, I get 50. But when I run this cell below, x is still 25. What is happening here? And that's because, so thanks for volunteering, but I'm just going to explain. So that is because, here's what happens. I call Fahrenheit. When I use a variable x, Python will replace the value of x with its value. Okay, so what happens is Python will actually do x, and then Python says, OK, x is 25. Call Fahrenheit with 25. Okay, now I go into my function, and x is 25 here. So this is kind of like saying, OK, I'm going to set x to be 25 in the beginning of the function because I called x with 25. And then I'm going to say, OK, in my function, the value of x is 10. Okay, so now I have x equals to 10. And then when I return, I do 10 times 9 over 5 plus 32. I get back out whatever I got before, which was 50 degrees. Any modifications I make to the variable x inside the function also stay within the function. Okay, so no, even though I changed x equals 10 inside the function, that does not affect the variable x outside the function. When I'm inside the function, you can think of it as just everything that happens in the function stays in the function. Cool? Now, not easy to understand, but I just want to make you aware of this because you're going to see this sometimes, and I don't want you to be confused. Okay, so some gotchas about the function. Cool. All right, I have more discussion questions. Let's do this. All right, so talk with your neighbor about what this function does, what type of input it takes in, what type of thing it outputs, as well as what the output is. And perhaps after discussing that, you'll think of a better name for this function than f. You can, of course, name your functions whatever you want. This one's named f. You can name yours, I don't know, Bulbasaur, Magikarp. But typically, you want to choose names that are helpful for you to remember. In this case, let's try to think of a better name for this function. Go talk with your neighbor.
We all have to see that's probably an array. So divide an array by a single number and multiply by getting the size of each item inside an array. And rounding just like that's the function name should be like set array. Set array items. Yeah, like if we have even this size, well, I don't know.
All right. Anyone have a guess as to what this mysterious function does? Yeah, in the third row. Your name and what you think?
My name is Gaurav.
Gaurav. Mm-hmm.
It basically converts an array of numbers into the percentage of the total of the array.
So Gaurav says it takes an array of numbers and it converts that array into percentages of the total. Is that
Yeah.
what I got? Okay, great. Yeah, so that is what it does. So in fact, if I pass in an array as s, I'm going to do s divided by sum of s. So this is kind of like each element will get divided by the total of that array. And I'm going to multiply all of that by 100 and then round it to 2 decimal places. So we're kind of computing like the percentages of each element inside my array. Okay. So what does this function do? We can say that it computes percents. What kind of inputs does it take in? It has to take in an array, and that array has to contain numbers. Okay. So if the array contains strings, I'm going to have a bad time. What kind of output will I give? Well, I get an array. I put an array. But when I do NPL round on an array, I still get out an array. So it's going to output an array also containing numbers. And a reasonable name for this function is probably like percents, because I'm computing the percents of each number in an array. So let's do that. So what I have here, so of course, so typically when we write functions, the best rule of thumb that I use in my personal coding is don't write functions that are not necessary, because it just takes work to write functions. What I mean is typically I'll just write code, and then if I find myself repeating myself a lot of times, then I'll go back and write a function and make it better. But typically, you don't really need to write a function for stuff you're only doing like twice or like once. Okay, so in general, write your code first, then you go back and you're like, OK, this is like really tedious. Let's write a function to make my life easier. Okay, so in this case, let's say I have counts, make array 3, and I want to say, OK, what percent of the total is each number? So I can do total counts.sum. And here I have 6. Okay? And if I take counts divided by the total, I get back like the proportion of each number from the total, right? So 1 is like about 17% of the total. 2 is like 1/3 of the total. 3 is 1/2 of the total, which is 6. Okay? Then I can round it. So np.round. And now I have like the percent rounded to 2 decimal places. I can multiply it by 100 here to get back like these as percentiles. All right. So let's say I'm doing this, and I'm like, OK, doing this a bunch of times. Let's write a function to do it. It's very easy to convert your code and put it into a function. All I have to do is say def percents counts. Okay. And typically, when I write a function, it'll be useful to you to kind of describe what the function does. Okay. So the way we describe what the function does is we use triple quotes. So quote, quote, quote. And you'll see here I have 3 quotes here, 3 quotes here. This is like one string that we call a doc string, short for documentation string. It just describes what the function does. So I can say, OK, this one converts counts to percent out of the total. That's just helpful for myself later, because I might come back in a year and be like, OK, what does this do? No idea. But I can read this and find out. Kevin?
Is there a difference between this and using the number sign for the comments? Is there a difference between the two?
So Kevin asked, is there a difference between doing this and doing like converts counts to percent? They kind of do the same thing. Now, we like to use this because it's just standard convention. Like people just are used to seeing it this way, and it has some like some minor benefits, which I'll show you afterwards. Yeah.
So does Python interpret that the same way as it does a comment? Like, does it interpret triple quotes as like not code, but a documentation or a comment?
Yeah. So what does Python do with this triple quote thing? So it treats it as if it were just a normal statement. So for example, if I write hello, Python would just say, oh, this is a string containing hello, and then move on. Right? So if I do hello and then x + 2, I get 27. Python just moves on past the string. Actually, in reality, Python will like look at that string and say, oh, this is a string, but then I'm going to move on. Okay, so it does evaluate it. It does treat it as code, but then since it's just a string, you don't do anything with it. It kind of just moves on. Okay. That's kind of what's going on behind the scenes. You don't have to worry too much about that, but it is good to know. Okay, so here I'm going to copy and paste in my code. Now here I can remove this line because counts I'm going to pass in as an argument instead of specifying it every time. But now I have basically my entire function. All I have to do is copy and paste my code. Total equals counts.sum. And then I'm going to round counts divided by total times 100 over 2. And I don't want to forget my return statement. If I don't put a return statement, percent, and I do make array, let's say like 246, I get nothing. Okay, so you see that? I didn't get anything out. That's because I did not put a return. So return array. Cool. All right, so let's take a look. So let's suppose I want to take my function, and I want to say, OK, right now I'm rounding into 2 decimal places. If I want to round it to 1 decimal place, I have to go back into my function, change this to 1, and then run it. And if I want to go back and round to 3 decimal places, go here, change it to 3, run it. It's not super great to do that every time I want to switch to decimal places. So when I find myself switching stuff like that, that's a good indicator that I need another argument in my function. So I'm going to take my function, and I'm going to add another argument, decimal places. Okay. Now I can replace the 3 with decimal places. And now I can call percents. Let's take my original line. And let's say I want to round to 3 decimal places instead of 2. All I have to do is pass in second argument for decimal places, and bam, I'm now rounding to 3. If I round to 1, decimal place. Okay, so that's kind of where you would use another argument. Now you might look at this and say, okay, well, I usually want to round to 2 decimal places. Only every once in a while do I want to round to 1 decimal place or 3 decimal places. I would prefer to actually call it the original way most of the time. If I try to take that original line and call it now, I'm going to get an error because my function now takes in 2 arguments instead of 1. In this case, I'm only passing in 1 argument, a single array. Okay? So I'm going to get an error, % missing 1 required argument decimal places. So it's missing an argument, it will complain. However, I can say, well, I'm going to call it with decimal places equals 2 most of the time. So what I can do here is if I add an equals 2, this tells Python, OK, if I call this function without specifying a second argument here, I'm going to just say decimal places is equal to 2 and move on. So if I do that, now it works. Oops, I need to run the cell. I run it. Now it works like this. But it also works like this. Okay. So if I don't specify, it'll say it's 2. If I do specify, it will let me replace it with whatever I pass in. Okay. So we've seen this before when we do sort. So if you remember, like if we have a table, and I do sort, right? I sometimes do descending equals true. Descending equals true, like that. That's actually one of these default, what we call default arguments in a function. Okay. So some convenient stuff to do, some convenient things to learn there. Any questions about that? Very well. I'm going to make a brief aside. Let's see how much time. Okay. I have to move fast. I'm going to make a brief aside and talk to you about the interact function. So before we were calling our functions like this, and we had to kind of like, every time we want to change the argument here, so let's say I want to call it with different things, 1, 3, 10. I have to like kind of make a new cell, run the thing, make a new cell, run the thing. There's an easy way to do that with a function called interact. The way it works is we call the function interact, and you pass in a function. So let's say I want to call my Fahrenheit function interactively, Fahrenheit. And then what I do in the arguments after that is specify the default value for each argument. So I'm going to say, OK, interact with my function Fahrenheit, and the x argument of Fahrenheit should be 50, right? So Fahrenheit takes in 1 argument x. I'm going to say start off at x equals 50. And when I run that, darn. OK, forgot some lines. I have to import. And we grab those missing lines. Go. Grab those import statements. OK, now I should be able to run this. And you'll see here that I get this nifty little slider. When I move the slider around, all it's doing is calling my function Fahrenheit with whatever value x is here. So this right here is a result of calling Fahrenheit on x equal to 28. If I move x to 100, let's see, 100. Oh, yeah, this is not changing because my Fahrenheit function is kind of messed up. Let me change it back to what it was before. When I run that, now I can move it around and see my Fahrenheit function output different stuff. This is exactly the same as calling Fahrenheit on 50, Fahrenheit on 72, Fahrenheit on 100, but this way I can just do it in a nicer way. Now, you're not required to learn this, and the reason why is because it doesn't work for all functions. So for example, if I try to use interact on a % function, it's kind of hard to make that work. So don't worry about it if it doesn't work, but it might be helpful for you to know if you want to call your functions and get this nifty little slider. If you recall all the way back in the first lecture, I made a little like text box where I can enter in like my own name and look at how many times I appear in Little Women. And then we looked at other people's names, like Chase's name. We looked at his name, how many times he appears. That little text box there is also done using this interact function. So just a convenient, optional thing for you to know. Maybe it'll be handy. OK, cool. So let's move on. OK, so just to recap, this is the syntax. Typically, we do underscore equals interact, blah, blah, blah. You don't really need this underscore equals, but if you don't put the underscore equals, you'll get some extra output in your cell that you might not want. So typically, we just do underscore equals because it's the most clean. Completely optional, might be handy. Okay. I'm going to move on because I'm running out of time. So let's take attendance. Right, gonna open up the attendance form. Done. Come on. There you go. Yes, the attendance theme song. Please fill out attendance now. Okay. I'm going to move on because I'm running out of time. So I'm going to briefly talk about apply. If you were in lab yesterday or today, you should be kind of familiar with the way it works. So what I'm going to do is I'm just going to quickly recap it and then move on to actually using it. Okay. So let's talk about apply. The way apply works is sometimes we have a table, and in that table we have columns. And sometimes we want to apply a function. We want to call a function on every value in that column. So for example, maybe I want to convert all my values from degrees Celsius to degrees Fahrenheit in my table. One way to do that is with apply. Okay? The way apply works is the first argument. So I call table.apply. The first argument is my function to use. And then my other arguments after that are my input column or columns. Okay? So here's how it looks. Table.apply. My function, so for example, Fahrenheit. And then my column label, maybe it'll be called degrees. Okay? So let me briefly go over how that works. Okay, so we call this apply. And I'm going to define a function called cutoff at 1,000,000,000. And this function takes the smaller of x and 1,000,000,000. Now, why will we need to work with such big numbers? I'm going to show you in just a sec. But what I'm going to do is I'm going to say, OK, if I pass whatever input I pass in, I'm going to return that value if it's lower than 1,000,000,000. If it's bigger than 1,000,000,000, then I'm going to return 1,000,000,000. Okay, so I have that. And if I call a function, cut off at 1,000,000,000, and I do 1, 2, 3, I get 1, 2, 3. But if I call it with 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, I get 1,000,000,000. OK? Cool. So if you'll remember from yesterday, we were looking at movies, the top grossing movies. Okay? So we have this table called top. We have a bunch of movies and how much they grossed. Right here, I've limited to movies to only ones that appear from the studio Fox. So we get less rows than before. But I'm just going to use this as a demonstration. So if I want to cut off this number to 1,000,000,000, or let's say this number, what I have to do is I have to take top.column, and then this is column number 0, 1, 2, 3, item 0. Now I have the actual number. Then I can call cutoff at 1,000,000,000 and do that. Okay, so this is not more than 1,000,000,000, but that's how I would call it on that. If instead I call it on perhaps Star Wars, I can take item number 2, and now it gets cut off at 1,000,000,000. So if I switch the item number here, I can call on different things. But really, if I have a column like this, usually what I want to do is call a function on every single number in here. So I might be tempted to do this. Cut off at 1,000,000,000 and just give it the entire third column. But if I do this, I will get an error. And that is because the types of my things don't match. Okay? So this is not a helpful error message. It says the truth value of an array with more than one element is ambiguous. It's not really helpful for me to debug. But my second step after that is to try to figure out what types of stuff I'm working with. Okay? Top.column3 is an array containing numbers. I look into my function, and I say, OK, well, x right here is a number. So a number is not an array. Python is not really happy about using min on comparing an array to another number. Okay, so I can't do this. So the way to actually call the function on every value in the table is to use apply. So I have top.apply. And I'm going to pass in my function. So there's my function. And I'm going to call it on the gross adjusted column. Okay. And if I do that, now you see I have an array containing one number for every value in my table. And these numbers are cut off at 1,000,000,000. So here's a cutoff. Looks like there's only one number that got cut off. Okay, so there's a cutoff. Oh, here's another one. Okay, so I have an array of all the numbers. If I want to add it back to the table as another column, That's not hard to do because I have the array. So all I have to do there is save this, cut off that, and then I can just say like top.width column. I'm going to call this cutoff, and I'm going to say add my cutoff array. And there you go. Okay, so add a column with my array. Now I have the cutoff numbers. So here I have 1 billion, whereas before it was over 1 billion. Yes, Kevin?
So that means if your function takes in more than one argument, that means in the apply function, you can put in more than 2 parameters, right? Is that true?
So Kevin's asking, like, what happens if I want to call a function on multiple columns in the table at the same time? We'll get to that at the end if I have the time for it. But for now, you can just know that it's possible. For now, I'm basically only going to work with functions that take in 1 argument and return out 1 argument. Okay, good question. Did you have a question, Alan? Same question. Okay, yeah. All right, so you'll notice here that the syntax of using this function is a little bit different than the syntax that we used before. Before, when I call a cutoff at 1 billion, I had to actually use parentheses and then like a bunch of zeros here. Okay, maybe like 1, 2, 3. Okay. Here you notice that I don't use parentheses. And that's because when I don't use parentheses, so cutoff at 1 billion, what I get here is I just get this thing that says function, blah, blah, blah. What this is saying is cutoff at 1 billion represents a function. It's not actually the result of calling the function. It's kind of like if you had a recipe to make a cake. You can either make the cake, if you put in the ingredients and you make the cake, you get back a cake as an output. But your recipe is like a sheet of paper that you have. So if you look at the recipe, it's like the recipe. If you look at the output of making the cake, you have like maybe like 3 or 4 cakes that you made with this recipe. Okay, so the function here is kind of like the recipe that we have, and just using the value without calling it is like saying here's a recipe by itself, not the actual cake that I made using the recipe. Okay, so that's the kind of thing that I have there. I can also do type on that and get the function. And it just so happens that because it's a function, I can also use question mark. If I use question mark, you'll see that I get the smaller of x and 1 billion. Where did that come from? That came from the docstring. So right here, when I define cutoff at 1 billion, I said, OK, this is the thing that describes what the function does. If I happen to use cutoff at 1 billion question mark, I get back this string. So it kind of helps me in the future when I'm trying to reference or figure out what this function does. OK, so useful stuff there. Any questions about that? All right, so let's see. Is anyone still taking attendance? Closing it. Closed. All right. Cool. So that's apply. Let's go through an example. So the example that I'm going to go through today is probably the first example that we've done in this class of prediction. Okay, so there's this guy named Sir Francis Galton. He's kind of strange. I'll talk more about why he's strange later. But basically, he was alive in like the early 1800s till early 1900s. He was really good. He was one of the first people to actually say, OK, maybe I can take some data that I had before and use it to make some predictions about what we have in the future. And he was particularly interested in heredity. In fact, he's considered one of the fathers of eugenics, if you're familiar with that term. Lots of negative connotations there, but he was interested in making predictions. Okay. Conveniently enough, he was Charles Darwin's half-cousin, so I guess it runs in the family. All right, so let's take a look at what he looked at. So I have this table here, predictions. This is Galton's data. Okay. So what he had here was he looked at a bunch of families, and he wanted to say, OK, given the father is 78.5 inches and the mother is 67 inches, how tall will the child be? Okay, so the child here is 73 inches. This particular family had 4 children. So these are the heights of the 4 children. Okay, so I have that data. As before, I can take that data and make a histogram. I'm going to select out columns. I want to look at the father column, the mother column, and the child height. And I want to hist. So now I have 3 overlaid histograms. Blue is the father, yellow is the mother, and like like sky blue is a child height. You'll notice something interesting here, which is that the father and the mother heights are a lot taller, like the heights of these bars, sorry, are a lot like taller up here than the child heights, which are kind of down here. Talk with your neighbor about why that might be the case. What does that mean? Go ahead.
There are more mothers than like 65 to 65 inches tall, or fathers have origins that are taller, as the children are a little bit more spread out. I mean, it's not that mothers genetics are not as complicated. It's not like it's not an figure, but even so, the word medallion, I guess it was still a little bit more spread out.
All right. So I'm going to cut you off because I'm running out of time. So let's talk about it. When the histogram has like tall bars like this, because again, we're working with a density scale, right? So if we're working with counts, on the other hand, we would say, okay, there are more maybe there are more fathers than children. But because we're working with densities here, what the taller bar means is that the number of fathers is more dense in this area than it's dense like down here, right? And the children are less dense overall. There's less children like clumped in one area here than there are fathers or mothers and their way of clumping, right? So this histogram is basically saying most of the fathers are kind of like within this short little bracket range, maybe like 67 to 72 inches. Most of the mothers are in this short little bracket range, maybe like 62 to 67. But the children kind of fall in this wider range here, maybe like 62 to like 72. Okay, so spread out over more heights in this case means that the bars will be shorter because height measures density, and we have less density. Okay, so let's take a look at this table again. So what Galton said was, I think that looking at the average of the father and mother's heights gives me a good indicator for how tall the child will be. Okay, so I'm going to take out, so what he did is he calculated that. So there's a mid-parent height. I'm going to take out this column right here and this column right here, because we're going to use it to make predictions. Okay, so let's take out Galton. And let's select out column number 3 and 7. So here I have mid-parent height, child height. Just to make it a little bit more clear, I'm going to relabel this column. I'm going to label the 0th column to mid-parent. And I'm going to relabel the first column to child. Okay, so all I've done there is grab out the 2 columns, relabel them. Call this heights. Okay, so there we have that. Now I can make a scatter plot. What will the scatter plot show me? Think about that while I make it. Except we don't have that much time because I made it. Okay, so what I have here is the mid-parent height on the x-axis and the child height on the y-axis. It looks like as the average height of my mother and father go up, the height of the children kind of go up with it. It's kind of like spread out here, but it looks like on average, if the mid-parent height goes up, the child height also will go up as well. Okay, so how can we use this to make some predictions? Well, if you're familiar with the regression line, there is this thing called regression line, but today we're going to do something a little bit simpler. All I'm going to do is say, okay, I'm going to look at, for my child height, let's say I want to predict my child height for a mid-parent height of 68. What I'm going to do is I'm going to take my data and say, take a little slice here of my points and then find the average child height within those points. Okay, so what that means is, take my heights. Let's say I'm trying to say, what will my child height be if my mid-parent height is 68? So I'm going to take the rows where the mid-parent height is between 67.5 and 68.5. Okay, so now I only have kind of like this slice of the scatter plot. What I'm going to do is I'm going to call this close to 68. Just save that in a variable. Okay? And what I'm going to do is I'm going to say, OK, my prediction for my child height is close to 68. I'm going to grab the child column and take the average. Okay, so all I did there was say, OK, if my midparent height is 68, grab a slice, find the average height within that slice. And now I have my child height should be around 66 inches tall. Okay, so just to kind of show you what's happening, I'm going to do some incantations. I'm going to draw some lines, just trying to illustrate what I mean. Actually, let me just copy it from here because it's not super important for you to know. Darn. Let's see if this works. There you go. Okay. So what I've done here visually is I've said, OK, take all the points in here, take the average. The average is the yellow dot here. Okay. So just visually what I did. Don't worry about this stuff. I'm just trying to show you visually what I did. Okay. So that's kind of how I'm going to make predictions. Now I want to make predictions for every single value of midparent here. Okay. So I'm going to say, OK, for every value of midparent in my table, make a prediction for what I think the child height should be. Okay. How do I do that? Well, if I want to repeat myself, if I want to repeat an action a bunch of times, typically it's good to make a function. Let's make a function. Define predict child. And I will say, so this MP stands for midparent. I'm going to say close points equals, and I'm just going to copy. So copy that. Copy that. It's not close to 68. I'm just going to say close. So close. Midparent is between. So this value right here needs to change because it's not always going to be between like 67.5, 68.5. So again, just make sure you know which parts are changing between function calls, which parts are not changing. So right here, this is changing. I don't want to look at just 67. I want to say, take my input and subtract 0.5, and then take my input and add 0.5. This gives me the slice for every input that I give my function. Okay, so there's my close. Now I'm just going to take that, copy it, and this changes to close, and I can return it. Okay. And now if I call predict child on my midpoint, which was 68, I get back 66.24. Okay, so got a function. Now I can predict a bunch of heights. I can predict the height for midparent as 70, 67. Okay, so now I can make a prediction. I can just change my input, get a new prediction. Now that I have a function, I can use apply to call it, make a prediction for every single row in my table. So I've got my heights table here. What I'm going to do is I'm going to apply. Let's predict child, okay, on my midparent column. And wait for that to run. It takes a while because it's looking through a lot of numbers, doing a lot of computation. In the end, I get an array of predictions. Okay. And again, to add as a column in my original table, I just need to take my heights. Heights, let's call it height with predictions. And do heights with column. I'm going to call it prediction. And I'm just going to take that and stick it in there. Okay, so now I've got that. Heights with predictions. So it's going to do some computation again because I'm running it again. But now I have predictions for every single midparent. And I can make a scatter plot to look at my predictions. Heights with predictions, I'll scatter midparent. And you can see here that the way that I do my predictions kind of looks like it follows this line going upward. So it does look like, to make a good prediction, as my midparent height goes up, my child height will also go up. Okay, that's all the time I got for today. I'll see you guys tomorrow.